Welcome to MathTopia Academy. My name is Holly, and today I am going to show you how to solve problems 16 through 25 from the 2026 AMC 8. Consider all positive 4-digit integers consisting of only even digits. What fraction of these integers are divisible by 4? Well, to start, we know we have a 4-digit number, and it's composed of only even digits, so 0, 2, 4, 6, and 8. In order for a number to be divisible by 4, the number created by its last 2 digits has to be divisible by 4. So that means that we only care about these 2 digits. Let's call them A and B. The number created by A and B will be 10A, because A is in the tens place, plus B, because B is in the units place. Since A is an even digit, that means that 10A must be a multiple of 20. Since 20 is divisible by 4, this means that 10A is also divisible by 4. So we actually don't even care about A either, since whatever it is, 10A will be divisible by 4. That means that we only care about B. In order for B to be divisible by 4, it can either be the digit 0, 4, or 8. That makes 3 possibilities for B out of the 5 total possible digits we could have chosen from. Since divisibility by 4 is only contingent on the last 2 digits, we don't care about these first 2 digits. And since 10A is always a multiple of 20 and therefore divisible by 4, we don't care about A either. That makes the information we have about B enough to answer this question, which would be D, 3/5. Four students are seated in a row. They chat with the people sitting next to them and then rearrange themselves so that they are no longer seated next to any of the same people. How many rearrangements are possible? So I'm just going to call these people A, B, C, and D. The first thing that I notice is that the 2 people sitting in the middle are each seated next to 2 other people. So person B, for example, is seated next to person A and person C. Whereas the people on the end, such as person A, is only seated next to 1 other person. This is important because suppose we have person A, B, C, and D, and when they move to their new configurations, person B sits in another middle seat. In order for them to sit next to someone different, they would have to be seated next to person D. So suppose person D moves over here. This spot right here would have to be filled by either person A or person C, but they've already sat next to person D, so this configuration would not work. So in order to get a valid configuration, the 2 people in the middle would have to move to outer seats. So for example, person B could move to the left and person C could move to the right. And then that leaves only one possibility for person A and person D to go. Person A would have to go here, and person D would have to go here. The only other variation of this configuration would be if person B moves to the rightmost outer seat, and person C moves to the leftmost outer seat. And then again, A and D would only have 1 spot to go. These right here are only 2 configurations. Therefore, our answer would be A, 2. In how many ways can 60 be written as the sum of 2 or more consecutive odd positive integers that are arranged in increasing order? Well, the first thing to notice is that 60 is an even number. This is helpful because we're working with odd numbers and we're trying to make a string of odd consecutive numbers that are equal to 60. An odd number plus an odd number will always give us an even number.
whereas an odd number plus an odd number plus an odd number will always give us an odd number. This is important because when making our strings, we can only have an even amount of odd numbers, since that will give us an even sum, like 60. An odd number of odd numbers will not work. Knowing this, let's try to start by making a sum using two odd consecutive numbers. 60 divided by 2 is 30, so we can start with 30 as a base. 30 plus 30 is 60, but how do we turn this into odd consecutive numbers? Well, by subtracting 1 from 30, we get 29, and by adding 1 to 30, we get 31. 29 plus 31 is 60, and this is a string of odd consecutive numbers, so this works. Moving on, we could try to create a string of 4 odd consecutive numbers. 60 divided by 4 is 15, so we could use 15 as our base. The only problem with this is that we cannot exactly use the same balancing method as we did above, because 15 plus 1 is 16 and 15 minus 1 is 14. 14 and 16 are even numbers, which does not confit our restraint of the numbers being odd. Another way we could try to work with this is bringing down the 15 and working around it to get odd consecutive integers. This would give us 17, 13, and 11. However, this sum is less than 60, so this does not work. If we try it the other way down and bring down this 15 and work around it, we have 13, 15, 17, and 19. This gives us a sum that is greater than 60, so this will also not work. Since our balancing method didn't work, and since keeping the 15 as a center and working around it did not work, it is not possible to create a sum of 60 out of 4 consecutive odd integers. So this does not work. Next, we can try creating a string of 6. 2, 3, 4, 5, 6. 60 divided by 6 is 10, so we could use 10 as our base. Since 10 is an even number, it seems like we can use our balancing method as we did over here. 10 plus 1 is 11, 10 minus 1 is 9. Working off of that, we get 13 and 15. And 7 and 5. This, in fact, does give us a sum of 60, so this is a valid solution. We can't create a string of 8 since 60 is not divisible by 8, but we could try creating a string of 10 numbers. 60 divided by 10 is 6, so we could use 6 as our base. Rather than writing out a bunch of 6s, I'm just going to start balancing so that I don't take up a bunch of space. 6 plus 1 is 7, 6 minus 1 is 5, and then working off of that we get 9, 11, 13, and 15. Working backwards we get 3, 1, -1, and -3. We should already see the problem here. We have negative numbers, and we can only have positive integers in our sum. So this is a solution that will not work. If we create a string of numbers that is longer than 10, negative numbers will keep on appearing in that sum to balance out the higher numbers. This is where we know we can stop. We have 1 good solution and 2 good solutions, so our answer is B, 2.
Miguel is walking with his dog, Luna. When they reach the entrance to a park, Miguel throws the ball straight ahead and continues to walk at a steady pace. Luna sprints towards the ball, which stops by a tree. As soon as the dog reaches the ball, she brings it back to Miguel. Luna runs 5 times faster than Miguel walks. What fraction of the distance between the entrance and the tree does Miguel cover by the time Luna brings him the ball? Okay, so I'm going to start by calling Miguel's distance that he travels M. And then Luna's path, since it's the distance from the park to the tree, will be D, and this distance will be D minus M. The question is asking what fraction of the path that Miguel walks. So we need to find how much Miguel walks over the total distance. Since Luna runs 5 times faster than Miguel walks, the distance that Luna covers will be 5 times the distance that Miguel covers. So 5 times the distance that Miguel covers equals the amount that Luna covers, which is D plus D minus M. Solving this, we get 6M equals 2D, and M over D equals 2 over 6. This equals 1/3, so Miguel covers 1/3 of the total distance. Next up, the land of Catania uses gold coins and silver coins. Gold coins are 1 millimeter thick, and silver coins are 3 millimeters thick. In how many ways can Taylor make a stack of coins that is 8 millimeters tall using any arrangement of gold and silver coins, assuming order matters? Lucky for us, these numbers are pretty small, so we can just do casework. Our first case is that we have 3 millimeters, which gives us 6 millimeters, and we need 2 more millimeters, so we can do a 1 millimeter coin and a 1 millimeter coin. Next, if we were to use 1 3 millimeter coin, then we would have 5 1 millimeter coins. Finally, we could have 0 3 millimeter coins and just have 8 1 millimeter coins. Since order matters, we need to account for that. So for our first option, we have 4 total coins, so 4 factorial, divided by 2 factorial since there's 2 3 millimeter coins, and 2 factorial since there's 2 1 millimeter coins. Then for the next one, we have 6 total coins, divided by 5 factorial for the 5 1 millimeter coins. And finally, we have 8 coins, so 8 factorial, but all of them are 1s, so divided by 8 factorial again. This equals 6, this also equals 6, and this equals 1. So our answer is 6 plus 1, which equals 13. And our answer is D.
Charlotte the spider is walking along a web shaped like a 5-pointed star, shown in the figure below. The web has 5 outer points and 5 inner points. Each time Charlotte reaches a point, she randomly chooses a neighboring point and moves to that point. Charlotte starts at one of the outer points and makes 3 moves. Revisiting points is allowed. What is the probability she is now at one of the outer points of the star? Okay, so we know that Charlotte starts at one of the outer points, makes 3 moves, and ends on one of the outer points. If Charlotte starts at an outer point, she can move either here or here, both of which lead to an inner point. So from an outer point, Charlotte must go to an inner point. When thinking the opposite way around, if Charlotte is to end on an outer point, that means that she must come from an inner point. So she must come from an inner point to get to an outer point. Now that we know this, we can start calculating our probabilities. The probability that Charlotte starts on an outer point is 1, since that's given information. The probability that she then moves to an inner point is also 1, since that's the only move. Now that Charlotte is at an inner point, though, she has some options. she can either move to the outer points or to the inner points. There's 2 out of 4 ways for Charlotte to end on an inner point, which would be 1/2. Charlotte is still at an inner point, so the probability that she ends on an outer point is also 2/4 or 1/2. This is now all the information we need to solve the problem. Multiplying, we get 1 times 1 times 1/2 times 1/2 equals 1/4. So the probability that Charlotte starts on an outer point and ends on an outer point after 3 moves is 1/4, or B. The integers from 1 through 25 are arbitrarily separated into 5 groups of 5 numbers each. The median of each group is identified. Let m equal the median of the 5 medians. What is the least possible value of m? Okay, so I've drawn out my 5 groups of 5 made through the numbers 1 through 25, where this is a group, and so on and so forth. The median of each of these groups would be the middle number, or this column highlighted in yellow. The median of the medians would be the middle of this yellow column, or this number highlighted in red. Our goal is to find the smallest possible number that could go in this red space. In order to do that, we should try to find all of the smallest medians possible. We could do this by putting a 1 here and a 2 here, which would give us a median of 3. These 2 numbers could be higher. Next, we could have 4 and 5 and a median of 6. These 2 numbers could also be higher. And then we could have 7 and 8, and this number is 9, where these 2 spaces can also be higher numbers. This is actually all the information that we need to solve this problem, because all of these numbers can be filled with higher numbers, but it doesn't matter what. Or it does matter, but it's not necessary to find the answer of this problem. Therefore, the smallest median we can have is A, 9. Lakshmi has 5 round coins of diameter 4 centimeters. She arranges the coins in 2 rows on a tabletop, as shown below, and wraps an elastic band tightly around them. In centimeters, what will be the length of the band? Okay, so we know that the diameter of these coins is 4, so the radius is 2. I'm going to draw in the center of all of these circles and connect their radii. Right here, 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 and here. This will be 2 plus 2 or 4 centimeters, 2 plus 2 is 4 centimeters, 2 plus 2 is 4 centimeters, and 2 plus 2 plus 2 plus 2 or 8 centimeters. I'm then going to connect the radius to the points of tangency of these arcs, or where the elastic stops. We can see that this length will be equal to this length will be equal to this length, and so on and so forth. So now the measures that we need to find are the length of all of these arcs. But how do we do that? Before we try figuring out, I'm just going to find the sum of all of these yellow pieces. We have this length plus this length plus this length plus this length, which is going to give us 20. So our total length of the band will be 20 plus whatever the total sum of these arc lengths are right here. All right, I'm going to erase this to try something else. Okay, so I'm going to draw a few parallel lines. I'm going to draw a line tangent here, a line tangent here, a line tangent to these 3 coins, and a line tangent to these 2 coins. We can see that these 2 lines will be parallel. So if we want to draw another parallel line, I'm I'm drawing a line tangent to the two circles above, and these would be parallel. And then I'm also drawing a line tangent to this circle right here and parallel to this line. So we would have something like this. Okay, now the arc lengths that we have is, just gonna get the highlighter, right here, 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 and here. Using all of these tangent and parallel lines, I'm going to try to move these arcs around. Since we have a bunch of parallels and transversals, we know that this angle is going to equal this angle. So this yellow arc is going to equal this arc right here. We know that this angle is going to equal this angle. So the green arc right here will be equal to this arc right here. And finally, we know that this angle will equal this angle. So this blue arc will go right here on this circle. It's actually very convenient because we moved all of our arcs to one circle, and we see that it actually is just the circumference of one circle. The formula for circumference is circumference equals pi times diameter. We know that the diameter of a coin is 4, so our circumference is 4 pi. Adding this to the perimeter of the connected radii, we get 20 plus 4 pi, or C. The notation n factorial is defined as the product of the first n positive integers. Define the superfactorial of a positive integer, denoted by n superscript factorial, to be the product of the factorials of the first n integers. How many factors of 7 appear in the prime factorization of 51 superfactorial? So 51 superfactorial will look something like this. 51 factorial times 50 factorial all the way down to 1 factorial. Now, clearly by the answer choices, there's going to be a lot of 7s in this prime factorization, so I'm going to start from a foundation and build upwards. The first time that we reach a 7 will be with 7 factorial, and we'll have this 7 in 7 factorial, 8 factorial, all the way up to 51 factorial. The next additional 7 that we will get is 2 times 7, or with 14. This additional 7 will be in 14 factorial, 15 factorial, all the way up to 51 factorial. The next additional 7 will be in 7 times 3, or 21. That will be in 21 factorial, 22 factorial, all the way up to 51 factorial. The next additional 7 will be in 7 times 4, or 28. This additional 7 will be in 28 factorial, 29 factorial, all the way up to 51 factorial. The next additional 7 will be in 7 times 5, or 35. This will be present in 35 factorial, 36 factorial, all the way up to 51 factorial. We're almost there. The next one is 7 times 6, or 42. This will be present in 42 factorial, 43 factorial, all the way up to 51 factorial. Finally, the next additional 7 we will get is in 49. This 7 will be present in 49 factorial, 50 factorial, and 51 factorial. However, one thing to note about this is that 49 is 7 times 7, so it'll actually have 2 additional 7s. So whatever we get here, we just need to make sure to multiply that number of 7s by 2. Okay, so now that we have all of our 7s, we just need to add up all of the numbers in this list, or how long these lists are. So we know that in our first list, we're going to have 51 minus 6, or 45 numbers. We will have 38 total numbers, 31 numbers, 24 numbers, 17 numbers, 10 numbers, and 3 numbers. However, we know for 49 that we're going to have to multiply the amount of 7s we have by 2, since 49 is 7 times 7. So I'm just going to write at the end plus 3, since we have 3 7s, but we need to add 3 more 7s. Now, to add this list, we can see that each time the number decreases by 7, which can be helpful when we're adding. So we have 3 plus 10 plus all the way up to 38 plus 45. We can create sums of 48 here. And since we have 1, 2, 3, 4, 5, 6, 7 numbers, we will have 48 over 2 times 7, plus this 3 at the end for the 3 extra 7s that we have. Doing this math out, we get 168 plus 3, which gives us E, or 171. Now, it's really important to notice this 49 right here, because a lot of people will choose the answer D of 168, which is not correct on its own. You need to make sure to add this extra 3 to account for the 7s. So our answer is E, or 71. In an equiangular hexagon, all interior angles measure 120 degrees. An example of such a hexagon with side lengths of 2, 3, 1, 3, 2, and 2 is shown below, inscribed in an equilateral triangle ABC. Consider all equiangular hexagons with positive integer side lengths that can be inscribed in triangle ABC, with all 6 vertices on the sides of the triangle. What is the total number of such hexagons? Hexagons that differ by only a rotation or a reflection are considered the same. Okay, well, the first thing I notice here is that all of these angles have to be 120 degrees, and the supplement of 120 degrees is 60 degrees, which means that the angle measure of these smaller triangles has to be 60 degrees. This creates 3 equiangular or equilateral triangles, which is helpful because if we know this side length, we can find these 2 side lengths as well. So actually doing just that, we know that this side length is 2, which means that these 2 side lengths are also 2. We know that this side length is 1, which means that these 2 side lengths are also 1. Then we can find the length of the side of this big equilateral triangle, which will be 1 plus 3 plus 2, or 6. Now, like I said earlier, it's really helpful that we have these equilateral triangles because by knowing this side length, we can find, and this side length and this side length, we can find these 2 side lengths, which will just be the same. And since we know these 2 side lengths, we can then find the measure of these lengths. So in order to find the lengths of all 6 sides of our hexagon, all that we need to know are the lengths of these 3 sides. Okay, another thing that's helpful to notice is that our hexagon has to have integer side lengths, and the smallest integer is 1. So this measure right here can be 1 or anything greater, which means that the sum of these 2 sides has to be 5 or less. So the sum of these two sides has to be 5 or less. In fact, the sum of any two sides of these equilateral triangles, these smaller equilateral triangles, has to be 5 or less. Using this information and the information from our answer choices, knowing that there is so few of them, we can just do casework. Okay, so I'm going to draw my first triangle. And to make sure that we don't overcount, I'm always going to make sure that this is my greatest side length, that this side length is less than or equal to this side length, and that this side length is less than or equal to this side length. Okay, so the smallest possible side length that we can have is 1, which means that this length is 1 and this length is 1. Another possible configuration is that this side length is 2 and that these two side lengths are also 2. Notice that so far all of our solutions work because if we take the sum of any two sides, we'll get a number that is less than or equal to 5. Continuing this, if we have a side length of 2, this side length can also be 2 and this side length can be 1. And lastly, if this side length is 2, this side length can be 1 and also 1. Now we can keep going. If our largest side length is 3, our next largest side length has to be 2, because 3 plus 2 equals 5, which is the greatest sum that we can have of any two of our smaller sides. So this side length can also be 2. Next, if this is 3, we can also have 2 and 1. And if this side length is 3, we can have 1 and 1. If our next largest side length is 4, then this side length can only be 1, because 1 plus 4 is 5, and anything greater would make this side length equal 0, which we don't want. So then this side length will also be 1. Now this is where we can stop, because if we create a triangle with any larger side lengths, like if this was 5, this side length would have to be 1, and we have 1 plus 5, which is 6, or greater than what these two sums would be. Again, this would create a length of 0 for one of the sides of our hexagon, which will not work. So we're done counting our cases, and we know that there's 8 of them, so our answer will be E, 8. I hope you enjoyed these video solutions. As you prepare for your next math competition, check out these other great resources now available on Amazon.